Hello everyone and welcome back. My name is Mr. Cobalt and in this video we're going to go over some mechanisms. So let's get into this. So in this video we're going to be going over how to derive a rate law from mechanisms. So here we have two examples. So right here, A, so we have I2 going into 2I. This is a fast elemental steps. So these are elemental steps that will add up to the overall step. So there's two criteria that you need to meet in order to uh, make sure you get the right reaction mechanism or the right rate law from the mechanism. First is all of the elemental steps. So these elemental steps should add up to the overall step. So for both of these, they do indeed add up to the overall step. And the second thing is that the derived uh, rate law must match what experiments say. So there's that. So for this video, we're not going to be given any experimental like data or anything like that, but I will go over the strategy that you want to use when you're trying to derive the rate law from the mechanism. Okay, so the first thing you want to do is look for the slowest step because the slowest step is going to be the rate determining step. It's the one that's going to determine what the rate law is going to be. So for the first one, we see that this step here from I2 going to 2I, and it's a fast step. And you can see that there's a double arrow here, meaning equilibrium. So since this step is really fast, this is going to reach equilibrium quickly. So same thing for this step. The second step, you have here 2I. Well, the I here is going to be then used in the second step to get to react with H2. So I plus H2 is going to give you H2I. And again, this is a reversible step and it's fast. So basically, this is going to reach equilibrium pretty quickly. And then the third and final step is the slow step. This is the rate determining step. And this is where the H2I is taken and reacting with I from here, right? So you got I again. So the 2I, I is going to be reacting again with H2I to form 2HI. And this is the slow step. Now, the important thing to remember is because these two are fast and they're reversible, these two are going to be in equilibrium. And so the rates of the forward and backward reactions are going to be equal to each other. That's going to be important because we're going to use that to help us do some substitution to get the rate law that we're looking for. Okay, so what do we do? So this is the rate determining step. So we got to write what the rate law for this elemental step is going to be. So we'll write all of the elemental steps for them, but let's start with the slow one. So the slow one is going to be the rate is going to be equal to, and also let us give k values to each of the forward and reverse directions. So since this is step number one, we'll call this forward step is going to be k1. The reverse step is going to be k minus 1, negative meaning reverse. Same thing for the second step. So this is the top one, the forward step is going to be K2, and the bottom one is going to be K negative 2. And since this is not reversible, we're just going to use the forward reaction. That's going to be K3. So we're going to write the rate law for this step here. All right, let me rewrite this so it's clearer. So this is going to be K3. Okay, so then using the rate law, writing the rate law for this step here is going to be the rate is equal to K3 times the concentration of H2I times the concentration of I. So that's basically how you write the rate law for each elemental step. It's just going to be the rate times K value times the all of the reactants raised to their stoichiometric powers. So here we have coefficients 1 and 1, so they're raised to a power of 1. Now, this is going to help us determine the rate law. So the rate law is going to be based on this, right? Because this is the rate determining step. So this is where we're going to get our rate law. Now, the rate law should have only the reactants here, H2 and I2, because this is the overall reaction. And so the rate law should have the reactants that are in the overall rate and not in the overall reaction and not in the individual steps. So you'll notice here that we have H2I and I. Neither of those are in the overall reaction. They're intermediate steps. So they're intermediate, so we got to get rid of them. And so that's where these are going to come in. The reversible reactions are going to come in. So let's start with the second one. So since this is a fast reversible reaction, that means the forward rate and the reverse rate are going to be equal to each other. So let's write the rate laws for each of those forward and reverse reactions. So the reverse would be the rate is equal to K2, that's the forward. So looking at the forward reaction, we're going to use K2, and the reactants is I and H2. So it's going to be multiplied by I, the concentration of I, multiplied by the concentration of H2, both raised to the power of 1, since the coefficients are 1 and 1. Okay, now what about the reverse reaction? So going this way, H2I is the reactant. So if we're going this way, we're going to use K negative 2. So the rate, and we'll call this rate 2, and we'll call this rate negative 2. That's going to be equal to K minus 2 or negative 2 for the reverse reaction for the second step. And going reverse, H2I is reactant, so that will be the concentration of H2I. And here's where the equilibrium comes in. Since we know that this is at equilibrium because it's fast, that the rates are going to be equal to each other. So if the rates are going to be equal to each other, then these are going to be equal to each other. So rate 2 is equal to the reverse rate minus 2. And then we just substitute these in for these. So here we'll have K2 times the concentration of I times the concentration of H2 is equal to K minus 2 times concentration of H2I. Now, the great thing about this is we can now arrange this so that we can substitute one of these in for substitute this in for one of these. So we want to get rid of the intermediates. We want to only have these two in our equation. We want to get rid of the intermediate. So this is going to help us. So what should we substitute? So here we have, this is our equation we're trying to get. So let's put a star next to that one. This is the one that is our rate law based on the rate the rate the rate determining step. So we have to use this as our rate law. So this is the one we're going to substitute into. So here we have H2I and we have I. Well, we have I and H2I. Well, let's substitute in H2I because you'll notice here we have I here as well and I2, so we can use that for I later. So we're going to substitute this in. We're going to solve this for H2I. So we're going to divide both sides by K negative 2. We're going to divide this by K negative 2. So that cancels out. So we get H2I, the concentration of H2I, is now equal to this. So it'll be K2 over K minus 2 all over I times H2. So now we can take this and substitute in for that. When we do that, we get the rate is equal to K3 times K2 over K minus 2. So we got that together. And then we have I, the concentration of I, times the concentration of I. So that's going to be the concentration of I squared. And then we got what's left. We got I and then H2. So that's going to be the concentration of H2. So now we have this as our rate law. So we got H2, which is in our overall reaction, but now we still have this I, right? We have I, which is not in this reaction. We have I2, but that's not the same as having I by itself. So here we have molecular diatomic molecule I, iodine in the I2 form, but here we have I, just separate atoms of I, which is what we don't want in our rate law. So we have to get rid of the I here. So now we can go back to and do the same thing for the first step. Since the first step is also reversible and fast, then we can use the fact that the rates of the forward and reverse reactions are equal to do another substitution. So let's go ahead and erase this, since we don't need this anymore. Okay, so we have our reaction step number 1. So we'll say that the rate of the forward reaction of step 1 is equal to K1 times, what's the reactant? I2. Oops. So that's going to be I2. And then the reverse rate, that's going to be rate of -1. That's going to be equal to K -1 for the reverse. And that's going to be I2I. So that's going to be multiplied by I, concentration of I squared. Now look here. So since it's in equilibrium, the rates are equal. So the rate of the forward reaction of step 1 is going to be equal to the rate of the reverse reaction of step 1. So if these are equal, these here, then these are equal. So we're going to substitute in K1 times I2 equals k minus 1 times I squared. Now, look here, we have I squared. We have here I squared. We can solve this for I squared and substitute. So here, if I divide both sides by k minus 1, so that cancels out, and I end up with I, concentration of I squared is equal to k1 over k minus 1 times I2, the concentration of I2. So now I can plug this in and substitute this for this, or I can substitute this in for this. So then this becomes the rate is equal to, and I have K1 here, so it's going to be K3 times K2 times K1 over K minus 2. I have K minus 1 on the bottom, so times K minus 1. And then this is substituted in for I2. So then I2, and then multiplied by H2 here. So now I have everything in terms of I2 and H2, which is in my overall reaction, H2I2, and that's what I want. I don't want any intermediates in my rate law. So I do substitution of those intermediates using the equilibrium reversible reactions of the fast steps, right? So now I can simplify this here, right? K3 times K2 times K1, I can just call that K, right? So then the ultimate final answer will be the rate is equal to K times the concentration of I2 times the concentration of H2. And that is the rate law for that reaction there. Now we could do the same thing for B. So let's go ahead and do part B. Okay, now part B is actually a bit easier because notice here that the slow step was the last step, right? So we had to, because it was the slow step was not the first step, then we had to do substitution to get rid of the intermediates. Because remember, the intermediates are here, but notice here that the slow step is the first step. And the slow step is the one that determines the rate of the reaction. It's the rate determining step. And so if it's the first step, that makes things easier because notice what happens. Here we have, if we write, we always start with the rate law for the slowest rate determining step because, again, the slowest step is the one that determines the rate law, okay, of the whole reaction. So here, the rate law of this elementary step is going to be rate is equal to, and again, there's no equilibrium here, so we could call this K1, and this is going to be K2. So then K1, the rate is equal to K1 times the concentration of NO times the concentration of Br2. So this is the way we would write the rate law for this step here. But notice that NO and Br2 are in the overall reaction. So NO and Br2 are in this law, so there's no more that we need to do. We don't need to substitute because there's no intermediates in our rate law from the rate determining step. So this here is the rate law for this mechanism, for this reaction here. And that's all you need to do. So that is the answer. We just get rid of the 1 there. And this is the rate law for part B. That was easy, right? If this was helpful, if you enjoyed this video, if this helped you in any way, then please like the video, share the video, hit that like button somewhere around here. Also, do me a favor, hit that like button. Also, subscribe to my channel. Do me a favor, help me out. Also, make sure you click on the notification bell up there and click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with or a topic you would like me to cover, put that down below. It would be my pleasure to do that for you. Thanks for joining me and have a great day.